So again, chapter 14, what this video is going to look at is something called reaction mechanisms. And this is pretty much brand new information. It's a step-by-step mechanism for how does a chemical reaction take place. So we have focused a lot first year chemistry about writing a balanced chemical equation, and we've expanded upon that this year as well. And now with kinetics, we've talked about the rate law expression, the integrated rate laws, so on and so forth. But in reality, how does A combine with 2B to get to this new product? So that's really what mechanisms are all about. And what you're going to see on your notes is I've written a lot of notes for you. So more so, I want you to pay attention to what I'm saying. And I have put another link or two up to kind of give you some background of this as well. So in your notes, you're going to see what I call a mechanism for this reaction. So this means this is step 1 and this is step 2. So A gets together with B to make AB, and then AB gets together with another B to make C. So for this mechanism, you might have what I call a slow or a fast step, meaning in any kind of situation, there's always some step that is going to impede your progress in any production that you have. So this is what I call K1 and K2, meaning for this reaction, there is a constant. For this reaction, there is a constant. So if I take a look at the first reaction, the rate of this first reaction is K1, A to the power of 1, B to the power of 1. And then the second reaction is rate, K2, AB to the 1, B to the 1. Now the good news about mechanisms is literally however many you have of each one of these substances translate directly to the order, okay? So if I have 1A and 1B in my equation, that means it's both of these are first order according to A and B. So that is why we will determine that the first step is my rate law, okay? That is because first off, it is the slowest step. So the slowest step is always going to determine how quickly something gets done. And then secondly, in the second rate, in the second equation, you have AB, which is something called an intermediate, meaning it's not one of the reactants and it's not a product. So that's why this one has to be the rate law for this equation. So there are some requirements for a mechanism to be legitimate, okay? They must always add up to give the overall reaction. A rate is always determined by what we call the slowest step, okay? And then rate cannot have an intermediate, okay, in order for it to work. So that is why you will see that this cannot be the rate law because of the fact that you have that intermediate in that equation. So how are you going to see these kinds of questions? Well, there's many different ways that I could put it. And so these are a couple examples so you could kind of get a better handle on this. So again, here is my overall reaction, and here is a mechanism, and the fast and slow step. Well, which one is fast, which one is slow? That's a whole other discussion that we could get into when you write your own mechanisms. But if I give you a mechanism like this, just know that this is the rate of the first reaction, this is the rate of the second reaction. So if I look at this rate law, K2, NO, BR2, and NO, that is reflecting how many I have of each one of these. So these are both first order, okay? And again, we don't write ones in chemistry. So, and this is my slow step, okay? But why can't it be the mechanism? So again, the question I might ask you is, can you defend why this isn't the correct mechanism? You could say, yes, it is slow. It is a slow step. Yes, it adds up. But what it doesn't fulfill in the requirements is you have that intermediate, okay? So a type of question you might see has to do with the fact that can you prove that it doesn't work? What works, what doesn't work in that situation? All right, so to the next page, okay? And this situation, okay? So I have H2 plus 2ICl, this is an L by the way, goes to I2 and 2HCl. What is the rate law? So if I give you this mechanism here, okay, H2 gets together with one of the IC, ICLs, and you have an HI, HCl. So the HI here is going to be your intermediate, okay? So your slow step does contain the two reactants, so that seems to be good. They are written as a one-to-one relationship, so they're both first order. So you would say, yes, that is an acceptable mechanism for this reaction. That is based on the fact that there's one H2 and one ICl in that equation. It is the slow step, okay? And it all adds up, okay? So all of those criteria are met in order for that to be a legitimate mechanism. So what if you had what we call an equilibrium situation? Now, we haven't talked too much about equilibriums, but you have seen me do it a couple different times. Anytime you have a double-headed arrow, what it means is the forward and reverse are taking place at the same rate, So if you think back to when we were talking about vapor pressure, we have both an evaporation and a condensing taking place. The point at equilibrium is that forward and reverse are taking place at the same rate. So if I have a first step here, so again, step 1, step 2, and I know my rate law is this. NO to the second order, so I need 2 NOs and I need an O2 in my slow step. So if I look at my slow step here, I have the N2O2 as my intermediate. So I got a problem here, okay? But because I have this equilibrium, I could kind of manipulate this to get to where I need to be, okay? So I know that the forward reaction, let's go down to here, okay? The forward reaction is going to be, again, K1, and the reverse reaction is going to be K2 for that first equilibrium. So then the third equation, which is really the second equation, is going to be a K3, okay? What I need you to focus on is, in the equilibrium reaction, the NO, there are 2 of them going forward. So that's why you have a 2 up here as a second order. The reverse reaction is the N2O2 going back that way. You only have 1 of those. So the forward and reverse reaction, since it's at equilibrium, is equivalent. So these 2 equal each other. These 2 equal each other. Well, if they equal each other, I could set them equal in an equation. Okay, so all I did was manipulate this down to here. Well, what can I do with that? Well, I could take the K2 and bring it over to here. So I have N2O2, I should have brackets around it, that confuses you, is equivalent to NO to the second order, okay? So please note that if I then take this expression and plug it back into here, okay, which is my slowest step as it is written, okay, I could then substitute in essentially the NO to the second order because these 2 are equivalent. So I could plug that in here, and again, that's K3, K1 over K2, which all comes out to be overall K, okay, so don't worry about the K's necessarily. And then I get the N2O2, which is the correct rate law for this expression, okay? So do note, again, this is a second order, and this is a first order reaction according to that, and that reflects the balanced chemical equation up here, okay? So realize that, again, equilibriums are very helpful because you could substitute in essentially the intermediate part here for what is over here on the reactants. So anytime you see an equilibrium, that's going to be a good tool for you to kind of look at,